So here we are asked the question, what is the pH of a solution when 18.25 grams of HCl is added to 214 grams of KiO3 in a 1 liter solution of H2O? We're going to start off by writing our balanced chemical equation. So to begin, on our reactant side, we have hydrochloric acid, which is HCl, and added to that, we know we have KiO3, and since this is a reaction at equilibrium, we will put our double arrows, if you will. And on our product side, we have HiO3 plus KCl. So now when I'm doing a question like this, I always like to have my values at a place where I can see them all nice and clearly. So here I'm going to write that I have 18.25 grams of HCl plus 214 grams of KiO3. Now what we're going to do is we're going to find the concentration of HCl. And our concentration, or molarity, is equal to the number of moles over the volume, which is liters. And this is equal to 18.25 grams. So here we're going to do mole bridge. So 18.25 grams of HCl over 1. And to find the number of moles, we're going to multiply. So 1 mole of HCl is equal to 36.5 grams of HCl. And now that we know that our solution is in 1 liter of H2O, we are going to multiply it by, or divide it by 1. And we're going to do the same thing for our KiO3. So we're going to find that our molarity is equal to the number of moles over the number of liters. So we have 214 grams of KiO3, and that is over 1. Over 1, and 1 mole of KiO3 is actually, in fact, 214 grams of KiO3, which ends up working out very nicely, especially for our calculations. And once again, we are going to multiply that by, or divide it, my apologies, by the volume, which is 1 liter. And now we can plug this into our calculators, and 18.25 divided by 36.5 is 0.5. So that gives us a concentration of 0.5. And this gives us a concentration of 1. So we have 1 molar KiO3 and 0.5 molar HCl. So now we're going to flip to another page, and here we are once again going to write our concentrations. So here we have 0.5 HCl, and our concentration of KiO3 is 1. Now it is important to remember that these concentrations are our initial concentrations and not the concentrations when the reaction is at equilibrium. So now in order to find the concentrations of our reaction at equilibrium, we will have to complete an ice table. So, as shown here, we're going to write out our equation HiO3 with our equilibrium arrows, and it goes into H plus or H3O plus. They are the same thing. Plus IO3 minus. And if you do not know how to complete an ice table, I will walk you through these steps, or you can go refer to another video done by one of our classmates. So our ice table is going to be separated into 9 parts. Well, 3 by 3 parts. We have our I, our C, and our E. And we know our concentrations for I as in initial, for HiO3 is 0 since it has not been produced yet. Our H plus, which is equal to HCl, is 0.5, and our IO3 minus, which is equal to KiO3, is 1. So the important thing to remember is for the ice table, the I is for initial, the C stands for change, as in the change in the concentration as the reaction goes to equilibrium, and the E is equilibrium. So what is the concentration when the reaction is at equilibrium? And it is important to remember that when doing any sort of calculations with reactions at equilibrium, you cannot use the initial concentration. You must go through the steps. So since we know that the H plus and IO3 minus is producing the HiO3, then HiO3 has a positive change since it is being increased. The concentration is going up since it's being produced. And our H plus and IO3 minus is decreasing since it is producing the HiO3 plus. So we have our initial concentration plus our change, which is plus X. And we have our initial concentration of H plus, which is 0.5 minus X. And we have IO3 minus, which is 1 minus X, since it is going down as well as H plus. So our next step is to solve for the X value. So we are essentially finding what the value of X is. So to do that, we can use our Ka expression. So and first we're going to grab our data booklets and look for our acid, which is HiO3. So just under the strong acids we can find, there it is, HiO3 with a value of 1.7 times 10 to the power of negative 1. So we can write out our equation. Ka equals the concentration of H plus times the concentration of IO3 minus. Since we know that our Ka value is 1.7 times 10 to the power of negative 1. So to fill out the Ka expression, we have 1.7 times 10 to the power of negative 1. And we know that at equilibrium, our H plus concentration is 0.5 minus X, right? Because we know that after the change at equilibrium, it's 0.5 minus X, and our IO3 minus concentration is 1 minus X. So now let's pull out our graphing calculators to solve for X.
So you take one side of your equation and the other side of the equation, and you plug them into your graphing calculator as two separate functions, and look for the intersect after you've plotted the graph. Once you plot the graph, you might have to change the window to find where the intersect is. Once you find that, calculate for the intersect, and that is your X.
So once your graph is plotted, go second calculate and intersect. Click right bound, left bound, guess, and there you have it, your point of intersection. And that point of intersection is our value for x. So you can go ahead and jot that down, that our x is equal to 0.27. Remember earlier when I stated that our H plus value is really just H3O plus? Well, here, this is when that knowledge becomes useful. Our next step is to take out our handy dandy table, and if your teacher has not already given you this table, pause the video for a quick second and copy down these notes because this is very important. So with our H3O plus concentration, we can figure out the pH value simply by taking the negative log of our H3O plus concentration. Perfect. Now our next step is going to be to solve for the concentration of H plus at equilibrium. So since we know that our concentration of H plus after the change, so at equilibrium, is equal to 0.5 minus x, and we just solved for x. So since our x value is 0.27, that means that our H plus concentration has to be 0.5 minus 0.27. Perfect. So 0.5 minus 0.27 gives us the concentration of H, and that is equal to 0.23. And back to the table, since we know that the pH of our solution is equal to the negative log of our H3O plus value, and that value is 0.23. So we know our concentration of H3O plus, and all we have to do now is solve for the pH. So the pH is the negative log of 0.23, and using your graphing calculator or scientific calculator once more, our pH is equal to the negative log of 0.23. Put that into your calculator, and that equals to 0.63827. So we will round that up to 0.64. Perfect. And there is your pH value. Congratulations, you now know how to solve for the pH value of a solution using an ice table. Mr. Addis will be super proud of you.